What are we having today? So we are having some exciting thing today, and for today's lecture, cvnlp, we will be wrapping up computer vision. And next week, we shall begin our journey in learning about natural language processing. So let's see what are we doing this week. So, no, this is not working. Okay. So this week we will be covering the last topic for computer vision, which is object localization and object detection. So after this lecture, I hope you'll get a better understanding or better concept of what image classification is, what object localization is, and what object detection is. So many of you have reached out to me during week 8 and asking me about your assignment. And some of you are being very ambitious, and I like that. But the thing is, object detection is an extremely complex task. Therefore, I do not encourage you to choose this topic for your assignment in cvnlp. Well, you can save that idea for your capstone or whatsoever, but definitely not for this cvnlp, yeah? So, not even object localization. So I hope after today's lecture, you will be very clear on why am I stopping you from that. I am not discouraging you, but it's just the amount of work and amount of computation power which you need in order to train a good object localization and object detection algorithm. Okay. So, what do we have today? So for today's lecture, we will be recapping a little bit on transfer learning because that's where we are left off in week 7. So under transfer learning, we'll be walking over the concept of freezing layers, where we did a feature representation transfer, and we will also be talking about fine-tuning. So the slides is a little bit different. I hope to give you a better context on what this transfer learning is, because I think transfer learning is something that we must know or we must learn in this modern age of computer vision. Okay, you must leave tailors knowing transfer learning. So yes, before you enter the actual workforce. Yeah. So then we want to talk about object localization. We want to talk about what is localization and how will the target variable y of a particular task object localization look like. So you will come to see that it is not as simple or not as straightforward as how we used to be, how we used to see, but this is really complex. And intersection over union, IOU, is ultimately the performance matrix that we will use to evaluate how good our object localization algorithm is. So then finally, we will talk about object detection. So object localization and object detection is entirely different thing. So under object detection, what we want to walk over are two main concepts. Ultimately, these are two main streams of research within this object detection. As we go through this object detection, you will come to know that this object detection is not as simple as it is because the research is still ongoing and we do not know how it will further advance into. Okay, it is a very, very huge task for a computer to learn how to detect object. Okay. So let's first start with transfer learning. So just a recap on what transfer learning is, because this is something that we really have to learn in this modern age. Because in deep learning, this is a technique where we try to transfer the knowledge that is gained from a particular pre-trained model on a large data set to a new or related task. So it can be applicable to whether related or non-related task, and therefore it is actually very powerful. So what in week 7's practical, I think what we have demonstrated is that this approach, transfer learning, regardless of whether we have done fine-tuning or just freezing layers, it helps to improve the efficacy and also effectiveness of training models compared to if we were to train a particular large neural network from scratch. So that is a reason why we have to learn this transfer learning. So what are some of the approaches of transfer learning that we can apply? So there are two methods as we have gone through in week 7. So first method is by freezing certain layers and unfreeze a certain layer. So in this case, what we are trying to do is actually to transfer the feature representation method. So what is feature representation? So we are actually transferring how this network extract features from the images. Okay, so and then we are retraining the classifier in order to for this network to learn to output the output that we desire. So this is freezing layers. Then we also went through another concept, which is fine-tuning. So we want to relax certain layers of the feature representation of feature extraction layers and ask this architecture to actually learn how to extract the features from our very own data set, our very own image data set. So this is a better illustration on what freezing layers and what fine-tuning is about. So freezing layers, I don't have to explain too much. So say for example, we have an extremely large image classifier architecture. So this is actually a VGG16 architecture. So what we are trying to do here is somebody else have actually used and take this architecture and train it on an extremely large data set. So this network has actually seen a lot of images in the world, which is labeled. So at the end of the day, this architecture is able to learn the features from most of the images that we supply and output 1,000 layers of classes. So now, what are we trying to do here is that we say, okay, so now I don't need you to output 1,000 classes of object, but instead, what we want is output predict the object classes of our own CV task. Say for example, in our lab session, we just want this classifier, which are able to output 1,000 categories to output 2 categories, whether an image is a cat or is dog. So this is freezing layers. So what we are trying to do is we will freeze all these feature extraction layers. We do not update the weights, W-E-I-G-H-T-S. So then we will remove the classifier, which is able to give you 1,000 output. And right now, we want to modify this classification layer to output only 2 classes. So that is freezing layers. So now another approach of transfer learning is fine-tuning. So on fine-tuning, the concept is similar to what we have just seen on freezing layers. So now this builds upon the feature representation transfer, where we will further fine-tune the weights of the pre-trained model on our own data set. So now say for example, these are all the convolution and max pooling layers that helps us to extract features from the images. So now, usually these front layers, the lower layers, are extracting simple features such as edges, rounded edges, corners, things like that. And as we go further into the deeper layers, these layers is then able to learn a representation of an item, say for example, a face, a human, hand, whatsoever. So right now what we are trying to do is we want to retrain these few high-level feature extraction layers to suit it to our own data set. And then with this feature itself, we want to train a classifier that would be able to predict the object classes of our own CV data set. So now in the lab, in the lab during week 7, we have also demonstrated how powerful it is, and it is able to further push the performance of our image classifier from 90% to 93%. So now this really is built upon feature representation transfer. So now what we are trying to do is fine-tuning the weights that we have. So these weights are ultimately the numbers that we have seen in the little boxes of convolution operations. Okay, so those are weights. So now, what are some of the principles or guidelines in order to choose whether we want to use fine-tuning or freezing layers? So there are 2 aspects to consider. So the first aspect to consider is how large of a data set do we have? And the second aspect to consider is how similar is our data set or image is to the one that is pre-trained. Okay, so now, say for example, we usually, the problem or the challenges of computer vision adoption is usually small data set. With a small data set, we are often overfilling the network that we are training. So now, in the case where we have small data set, these freezing layers will then come handy, as in we are trying to use a pre-trained model on large data set and adapt it so that it can extract features or learn the representation of this extracted feature to the relevant classes that we have. So in the case where we have small data set and our data set can be very similar or it can be very different. So in these cases, we can then decide whether we want to fine-tune or we want to freeze certain layers. So this is some guideline on how do we choose whether we want to freeze or fine-tune layer. So now, because we have two aspects, and very often, the only aspect that we will consider is on the size of the data set. So the rules of thumb is, whenever our data set is small, we will then go with freezing layers. So if freezing layers is able to give us sufficiently good results, then we can then proceed to fine-tuning certain layers to see if it improves the performance further. Okay, so in the case with very small data set, freezing layers. In the case where we have larger data set, we can then retrain more layers to prevent overfitting. Okay, so these are usually two of the cases that we encounter in real life. So that is all I want to cover for transfer learning as a summary. This is a concept that is heavily used. How do we leverage on the trained models to build models for new tasks? New tasks where we have relatively small or specific use cases. So this is suitable for tasks with very limited labeled data, and it is solving overfitting issues, and freezing layers, fine-tuning are two main approaches in this transfer learning. Any questions so far? If there's no question, so when we try to freeze the layers in transfer learning, the weights and biases in those layers are not updated during training. Is that true or false? That's true. So that means when we are trying to freeze those layers, the layers which are that are frozen, will maintain their weights. So these weights are actually the knowledge that it has learned. So how do we come about to understand these weights is, you will need to have some basic idea about what neural network is about. Ultimately, this neural network is learning the weights. So freezing layers is generally preferred over fine-tuning when our new task is very similar to pre-training tasks. Is that true or false? So the idea is pretty simple. So freezing layers is preferred when the new task is similar, because we know that the pre-trained model can already extract the features from our images themselves. Therefore, freezing layers usually works very, very well when our new task is very similar to the pre-training task. Okay, so you get the concept about when freezing layers is good and when fine-tuning is better. Okay, so now the next topic that we want to discuss is object detection. So now we have talked about this image classification. Image classification has become the foundation for object localization. And this object localization is the foundation of object detection. So all of this is trying to teach a computer a different task which human can do with the blink of an eye. So what are they separately? So the context about three of the terms over here, image classification, object localization, and object detection, is about how do we train a computer system to mimic humans' ability to scan through pictures or images. So say for example, I can easily pick out where are the empty seats as I scan through this classroom. But how are we able to enable a computer to do that? So that is an object detection task. But before we come to object detection, there is a bigger challenge to resolve, which is localization, because the foundation or the principle of detection is the ability to localize a particular object. So now let's try to understand some terminology about this object localization and object detection. So what are localization and what are detection? So now we have seen a lot on classification. So now classification is about taking one image and let this system to decide which class does this item belong to, does this image belong to. So now localization is about giving the ability to computer to locate the actual item inside that image itself. Okay, so now one additional thing to learn for the computer to learn, additional task for the computer to learn, is the ability to draw this red box. And this red box over here is called a bounding box. Okay, so object localization, it refers to identifying the location of an object in the image. For example, it locates the bounding box as well as the class of the object itself. So now we have now come to another bigger idea, that is object detection. So when we talk about this classification and also localization, we are often training this computer system based on very clean image which contains single object only. But what happens when we have a screen or an image that consists of multiple items? So then we want this system to be able to put a bounding box and classify every single thing in that particular image. So that is object detection. So it is very complex, as in what we are trying to resolve here is, where do we scan? If we were to scan every single pixel, would it be taking too long for this item to scan? So if we do not scan through every single pixel, will we be missing any particular object within that image? So those are the questions or the mechanism which the researchers is trying to resolve in the field of object detection. So there are two types of object detection method. So one of them is to put boxes around the detected object, and another type is instance segmentation, where we want to be able to associate every single pixel to the class that it belongs to. So now it is very different here, because if we want to enable some task which requires precision, say for example, can we automate the process of surgery to reduce human error? Can a machine perform better in removing tumor from a human's body compared to human's hand? So in these cases, we will actually require precision to the dot of every single pixel, which requires instance segmentation. And this is the difference between detecting object using bounding box and detecting object using instance segmentation method. So what we just covered is the difference between localization and detection. Localization is pretty simple, where we have a relatively simple type of image where we are trying to locate one single object in a particular image or in a particular frame. But when it comes to detection, what it means to us is be able to locate every single object within one image or one frame. Okay. So that's the difference between localization and detection. So now we are going to start with classification with localization. So what's the concept behind classification with localization? So it takes 2 steps for this computer to actually learn how to classify and locate a particular thing. So step 1 involves image classification. So now, say for example, this is something that we are already familiar with. That is, we have an image classification architecture here. So what it is trying to output here is the score of the item which we are trying to predict, which we want this system to output. So then what it gives us is the correct label of the particular object itself. So it involves image classification. So what it involves here is the last layer, the final layer of this convolution neural network is usually a softmax unit that outputs the predicted class of an image. So now say for example, we have an image of a snow scene and there's a truck at the middle of the image. So now what we are trying to do is first identify that, hey, this image belongs to a truck or a car. And yeah, how do we resolve the bounding box? So then what we are trying to do here is, yes, we can train this CNN to output the class scores in order to give us a prediction of whether, say for example, if this is used for an autonomous driving. So the common item that we wanted to predict would be pedestrians, car, motorcycle, or it's neither of those. So it's background. So then it gives us some class score. What we are trying to do here in localization is, can we then modify the final softmax layer to give us some location values. So say for example, we just covered that. So in a self-driving car example, our object categories may include pedestrian, car, motorcycle, or none of the above. So what we are trying to do is we are having this CNN to output the class scores. So now these categories represents the classes of the system that needs to identify. So then the softmax output will give us the possible outputs corresponding to the 4 classes. Our output is usually Y equals to some probability of whether it is class pedestrian, class car, class motorcycle, or class background, none of the above. Okay, so it depends on how we formulate this output. We can also output it as C1, C2, C3 because the last one is actually none of the above. Okay, so now in this case, what we are likely to see would be this C1, C3, and C4 will give us a relatively small probability of 0.0 something, whereas this C2 is going to give us a relatively higher value, which is close to 1.0. That's what a classification proportion of a localization task would do. So the step 2 is how do we add this localization task into the CNN architecture. So what we are trying to do here is to say that we can actually treat this as a regression problem that gives us some continuous value of a geometrical position. So now what we are trying to output is, instead of just providing the class score, now we want to provide 4 coordinates that consist of x, y, width, and the height. Okay? So what we are trying to do here is to modify the output of this CNN architecture to adjust it to output additional units that represent the bounding box. So that will give us the correct box. So now say for example, if you were to output this box, we will then have a central point of the bounding box that is represented by Bx and By. Then we want to be able to know what is the width and what is the height of this bounding box. So that gives us another 2 parameters, which are width BW, and height BH. So then it complicates our output of Y into, say initially we have just C1, C2, and C3, and now with localization, we are adding in additional output, which are Bx, By as the central point of this bounding box, Bh and Bw as the width and height of the bounding box. So now you also see one additional term on top of this output. So this output is giving us the bounding box location, that is a continuous variable, as well as C1, C2, C3 as a classification output. And what is this PC? So this PC would be an indication of whether this image consists of an item or not. So it is equals to 1 or 0. So sometimes it will detect, or we'll come to that later, where what we are trying to do is to select search for this object. Whenever we are trying to search for this object, we are searching it from boxes to boxes. So there will be an instance where we are sliding this bounding box through a certain region where we do not have any item. So in that case, this PC will be 0. And whenever it encounters the edge of a particular object, it will then say yes. And how high is the probability of the item within that bounding box that it is trying to scan. Okay, so now we have already covered this, where what we are trying to do is to treat this localization as a regression problem, which is able to help us output some continuous values that represent the box coordinates. So yeah, this is the concept of classification with location. At the end of the day, what we are trying to learn from here is expanding the image classification task into 2 tasks. So now we want to be able to predict the correct class of the item, and we want to predict the correct box which consists of the item, and that is classification with location. Okay, so now we are talking about a whole new concept here. We know that we are adding so many predicted output into our target variable. It's not as simple as item A, item B. It is not as simple as a series of value anymore. It is about a combination of things which we are trying to train at the same time. So now what we want to walk through is the basic concept of the components of target variables Y for this classification with location, as well as the loss function, and how do we measure how good this bounding box is. Because as we work on classification, we know that in order to decide how good a classification algorithm is, we can just simply quantify how many correct prediction that it has produced. So now how do we actually measure the performance of classification with localization? So that is intersection over union, which we'll come to that. So now we have talked about this center point, where we will put that as Bx and By. So that's the location of a center point of the coordinates of the center point of our bounding box. Then we have the width as well as the height that parameterize the bounding box. So now say for example, if we were to have a 1 by 1 image, we have 0, 0 at this point, 1, 1 at this point. So then our Bx and By would probably be 0.5 versus the height, which is 0.6. So then this will consist of the width, which is about 50% of the entire image. So that would probably be 0.5, and this would probably be 0.3, something like that. So what we are trying to do is this algorithm must be able to output these values as continuous value, and they have to be a square box. So that's parameters of our bounding box that we want this network to be able to learn at the same time give us the classification, the class of the object. So we have also run through how do we define the target variable. So this is how we write the target variable for a multi-class image classification problem. So what we are trying to say here is y equals to class 1 to class I, and with this T refers to transpose. So now if you were to transpose this matrix, we will be having y equals to C1 to C4. So Ci is the probability of a particular ith class, and if you were to have this network is trying to figure out the probability of every single class that it has predicted. So then the output of that particular item will be the one or the class with the highest probability. So that's target variable for a multi-class image classification problem. So now object localization includes more and more parameters which help us to define whether there is an object, PC, probability or confidence of an object within that bounding box, as well as the coordinates of the bounding box. And finally, adding up to the probability of ith class the object belongs to. So now these are all the parameters that we will be having in training a particular of one data point itself. Okay, so now in the case where we are training a localization algorithm, what we need to have is an image with all of these parameters within it in order to train a network. And in the case where we want to use the network to predict the output, then these are all the output that it should give. So this is the idea of the target variable of a particular object localization. So now just so imagine if we have a localization network trained on ImageNet. So then this matrix will be inflated into C1 until C999 or C1000, depends on how we formulate the output. Okay, so it is going to be extremely large, and therefore it will take time for us to train and to implement. So that is target variable for object localization. So I guess we just went through this one, and these are additional information for your revision. Okay, so let's take a look at an example. Say for example, we have a self-driving car. We are trying to train a localization algorithm for a self-driving car. So what we are trying to do is for this system to be able to differentiate between pedestrian, car, motorcycle, and background. So there are two situations. One, which is the road is clear, you can just move forward. One is there is a vehicle in front of you, and we want to drive another action of this autonomous system. So this is how it would look like. Say for example, whenever this system sees this screen or this image, what it's trying to output is, say, probably there is a car, the probability is high, it's 1. So now, we also have the bounding box, which shows us the coordinates of the item itself in order to help us to steer our car. Then, it is trying to say, okay, the probability of this item being a pedestrian is 0. The probability of it being a car is 1. And the probability of it being a motorcycle is 0. So then, this output will then be used to gear further programming of how this vehicle should be driven. Okay. So then, what if it has scanned through the entire image and did not find anything of interest? So now what we are trying to say is the probability of it having an object, having any of this object, pedestrian, car, motorcycle, is 0. And we just don't care about the rest of the parameters itself. So say, if let's say you have detected that PC is equals to 0, then we can just forget about the rest. So now comes the bigger question on how do we optimize the training? Because whenever we are training an algorithm, it is always about an optimization problem. What does optimization problem mean? Optimization means whenever we are training an algorithm, what we are trying to do is to reduce the loss function. If you still remember from our lab, where we see the loss function reducing from first epoch until the further epoch. So now, if we do not have a matching output between there is an object and there is not an object, so then how do we measure the loss function? So now, let the values of the target variable be represented as in y1 until y9 on all the parameters. So now, the loss function, there will be two parts of a loss function. So whenever it sees an object, it will follow this tabulation to calculate the loss function. And whenever it finds that y1 equals to 0, it will then use this formula to tabulate its loss function. And therefore, there are two algorithms in order to calculate the loss function. So loss function can be understood as a very simple term, which is error. How much error is it making? So this is just a very simple representation on how do we measure error. That is taking the predicted output y hat minus the expected output, the actual values of it. So this will give us the error or the loss function of object localization. And there are a lot of algorithms behind this calculation. And in this class, we just want to give you an idea of this loss function for localization. So now that's on how we measure error for our algorithm itself. So now the next question is, how do we evaluate how good our object localization is? So now we can't be training a localization algorithm that gives us an output as perfect as where this object is located. So say for example, this is the ground truth bounding box, and our algorithm is giving us this output, the one in purple color. So the next question is, how good is this bounding box? We want a quantification measure to measure how good this bounding box is, and therefore we are using the intersection over union. So what does this intersection over union mean? So this intersection over union is usually used to measure the performance, where we are trying to take how much area of the output bounding box overlaps with the ground truth, divided by the total area of the output bounding box and the ground truth. Okay. So now say for example, if we have a very high overlapping and with a relatively smaller bounding box, we are trying to maximize the area of overlapping versus minimize the area of union. So in those cases, we will be getting a value which is relatively large, larger than 0.5. So in that case, we will say that, oh, this is probably a good bounding box. So now in computer vision tasks, we usually set a score of IOU to be 0.5 to be a legitimate bounding box. So now say for example, if you were to put this bounding box across this, multiple bounding box across this image, it is going to give us multiple boxes that consist of an item. So now how do we enable this algorithm to only output one bounding box? So now this concept is called non-max suppression, where we are trying to take the box with the highest value of IOU. So a high value of IOU represent how good a bounding box is. But there is some pitfalls. Say for example, if we have a relatively small bounding box that sits within a ground truth, so then it inflates the values over here, and whatever that we are assuming will be invalid. So these are also some of the area which people are trying to resolve in this localization problem. So in short, in summary, in object localization, our target variable y defines what the model should predict. For example, the presence, the location, and the class of object. This loss function measures how wrong or how right the model is, the error. And finally, this intersection over union evaluates how well our bounding box would overlap with our ground truth. So the target variable y in object localization task typically includes bounding box coordinates for the object only. Obviously false, because it is supposed to tell us the presence, the box, as well as the class of an item. So a low IOU score suggests a significant mismatch between the predicted and ground truth bounding box. Yes, that's right. A low IOU is the one that we do not desire. So now we want to talk about the next and the final topic here, which is object detection. So under this object detection, the problem that we are trying to resolve or trying to teach the computer system is we are very familiar with classification, where we are trying to determine what object does this thing belong to in a picture, as well as what item or what class of object does this belong to within a bounding box. So that's image classification and localization. So now, what happens next is, how do we teach this computer how to detect item? As in, to mimic how our eye scans through the entire room. Okay, so that is a question of where do you look? Okay, so there are two concepts that we have. There are two concepts and two main streams of research within this research area on teaching how this computer should look. As in, do you look through every single part of an image or within a frame, or do you just look at a certain area? If you were to look at a certain area, then which area do you look at? So now, there are two streams. First one is sliding window detection. In the sliding window detection, the philosophy is that we want to look through every single part of this image to identify whether there is an object within the image or not. So this sliding window detection is this line on top here. So it is a one-stage detector where it is trying to output the Y, which we just discussed. It is detecting the probability, the bounding box, and also the item, and in one stage. So that is one-stage object detection. And some of the very famous architecture within this sliding window detection are YOLO, single shot detection, so far and so forth. So one of the most famous one will be YOLO, and it is one of the earliest architecture that is available riding on this sliding window detection. And there is another stream of researchers which are trying to say that this sliding window detection is inefficient. It is taking so much time to train and learn, and therefore we should use another mechanism to detect object, that is region proposals. So as the name suggests, this region proposal means we find a mean to try to tell this algorithm to locate an object only in a certain part of an image. So then the principle of this, to enable this, is then instance segmentation, where we can try to produce some blobs over an entire image, and this particular architecture will just predict or try to search for object within those parts that consist of a blob. Okay, so now that is region proposal. So under region proposal, there are several architecture. So starting from the RCNN, fast RCNN, faster RCNN, and so far and so forth. So we are going to look into stream 1 and stream 2 of research. So now in this sliding window detection, the mechanism that it takes is it will scan through the entire image systematically using one sliding window. Say, for example, we have an image. What we wanted to do is then to produce a window. So a bounding box, a window or a box for this algorithm to scan. So what it does here is it will scan through this corner area, and it says probably the PC belongs to 0, and then the rest just don't care. So then it strikes through another strike with a predefined strike length. So say, for example, we want a strike length of 10, which skips to this region. So then it will also give us an output of PC equals to 0, so far and so forth. So it will scan through the entire image until it produces some boxes with PC equals to 1. So then what it is trying to output here is, after scanning through the entire item, it will produce the bounding box which has an item with the highest IOU. So then what it does is, it doesn't stop there. In a sliding window detection mechanism, what we do is, we will then slide a bigger window through this image to ensure that we are not detecting an item which is smaller of the item itself. Okay, so now what it does is, it will take a larger window and slide through the entire image, so far and so forth. So now, in this kind of architecture, what we are trying to emphasize here is that we are not missing any single item within the object itself, because we will be scanning through small item, large item, with different size of sliding window. But the thing is, we are spending so much time, for example, in this image, just to locate 2 cars. And we have to scan through so many regions which doesn't consist of an object. So this can be phrased as, it can be computationally expensive because of a large number of window positions to evaluate, especially for high resolution image. The higher is the resolution, the more it has to slide through in order to detect a particular object. So there are 2 very common architectures when it comes to this sliding window detection. So YOLO and single shot detection. These are something that we have to know. So now what YOLO does is, it will divide this image into a grid and predicts the bounding box and class probability of each single cells. So then this single stage process, as compared to the single shot detection, is that it allows for faster inference compared to the single shot detector. So now this SSD is trying to resolve a problem that this YOLO could not resolve. So now say, for example, if you have 2 items that overlaps, so one in the position of one in a vertical position and another one in a horizontal position. So then this item could have a same center point. These 2 items can have one same center point. So in this case is where YOLO must choose between one bounding box.